Hello students, today we will discuss about transportation problem. We have already learned linear programming problem. You know, in a linear programming problem, there is an objective function which is linear and whose value is to be optimized. This optimization is done subject to some linear equations or inequations which are called constraints. Also, there are some non-negativity restrictions. We can solve linear programming problem using simplex method. Now, transportation problem is a special class of general linear programming problem. From transportation problem, an LPP model can be formulated and can be solved by using simplex method. But transportation problem has its own solution method which is independent of the general problem and which is much much easier than the simplex method. To describe a transportation problem, let us consider that a transport company has won the tender to supply garments to different outlets of, say, Reliance Trends all over India. So, this company has to collect the garments from different factories which are also located at different parts of the country and then has to deliver them to the different destinations. The company will do this whole work in such a way that the total transportation cost is minimum. So the objective is to transport various quantities of the product, that is the garments manufactured at several factories which are also called sources or origins, to different destinations, that is to different outlets, in such a way that the total transportation cost is minimum. This is the objective of transportation problem, that is to minimize the transportation cost. Now let us first represent the problem graphically. There are M factories, that is sources, where the garments are manufactured. The sources are usually denoted by O1, O2, O3 up to OM, or simply by 1, 2, 3 up to M. Let the production capacity of each factory be A1, A2, A3, AM. Now let there be N destinations, that is outlets. These destinations are denoted by D1, D2, D3, Dm, or simply by 1, 2, 3 up to N. Let B1, B2, B3 up to Bn be the demands of the destinations. Now, let Cij be the transportation cost for shipping 1 unit of product from ith source to jth destination. That is, C11 is the cost of shipping 1 unit of the product from the source 1 to the destination 1. Similarly, C12 is the cost of 1 unit of shipping the product from source 1 to the destination 2. In this way, CMN is the cost for shipping 1 unit of product from mth source to nth destination. So the objective of the company is to supply the required amount of each destination from one or more sources so that the total transportation cost remains minimum and at the same time the total requirement is fulfilled. Now let X11 be the unit delivered to the destination D1 from the source O1. Similarly, X12 be the unit delivered to the destination D2 from the source O1. X1n be the unit delivered to the destination Dn from the source O1. Similarly, Xmn be the units delivered from the source M to the destination N. That is, Xij be the unit delivered to the destination Dj from the source O. Therefore, the total transportation cost is summation over I from 1 to n, summation over j from 1 to n, Cij Xij. And also, from the source 1, the total unit delivered is given by X11 plus X12 plus X13 up to X1n, and this must be equal to A1. At the same time, in the destination 1, total units delivered from different sources is given by X11 plus X21 plus X31 up to Xm1, and this must be equal to B1. So we can write summation j equal to 1 to n Xij is equal to Ai. That is, total units delivered from the source Ai must be equal to summation Xij over j equal to 1 to n. And also, summation Xij over I is equal to Bj. That is, in the destination Bj, total units can be delivered from different sources is equal to summation Xij over I. Obviously, all Xij's are greater than or equal to 0. These Xij's are called the decision variables. Also, these are called the allocations. So, in a transportation problem, the transportation cost or shipping 1 unit of product from each source to each destination is given. Also, the capacity of each source are known, and the demand of each destination are also known, and it is to be find and we have to find the amounts to be shifted from the sources to the destinations for which the total cost, that is Cij xij, summation over j and summation over I is minimum. This is the graphical representation of the transportation problem. Now the corresponding LPP, that is the linear programming problem of the transportation problem, is summation Cij xij. This is the objective function. That is, we have to minimize the value of this function subject to the constraint equations xij summation over j equal to 1 to n is equal to ai for I equal to 1, 2, 3 up to m, and summation over xij over I is equal to bj for j equal to 1, 2 up to n, with the non-negativity restrictions xij is greater than equal to 0 for all ij. Thus, we get number of constraint m plus n, number of variables m into n, that is the decision variables xij. Now, if total supply equal to total demand, then one constraint is redundant. So, for any feasible transportation problem, we have exactly m plus n minus 1 non-negative decision variables. That is the allocation satisfying all the conditions. If the number of non-negative allocation is less than m plus n minus 1, then the solution is said to be degenerate. A transportation problem is completely defined by this table. Here O1, O2, OM are the origins, and A1, A2, AN, AM are the capacities of the origins, and D1, D2, Dn are the destinations, where B1, B2, Bn are the demand of the destinations. And in the entries in the cells are the unit transportation cost, that is Cij is the unit transportation cost to shift unit item from the origin Ci to the destination Dj. Now we are going to discuss about different types of transportation problem. There are two types of transportation problems. One is called balanced transportation problem, and the other one is unbalanced transportation problem. In balanced transportation problem, total supply equal to total demand, that is summation Ai is equal to summation Bj. And in unbalanced transportation problem, total supply is not equal to total demand. But this type of problem cannot be solved. We have to first transform the unbalanced problem to a balanced one by adding row or column. This type of problem will be discussed in our next classes. The solution of a transportation problem is obtained in two phases. In the first phase, we obtain an initial basic feasible solution, and in the second phase, we convert this solution to an optimal basic feasible solution. To find the initial basic feasible solution, there are many methods. Among that methods, we will discuss about 5 methods in details, that are Northwest Kerner method, least cost method, column minima method, row minima method, and Vogel approximation method. And the optimal solution can be obtained in by two different methods. One is called stepping stone method and another one is called modified distribution method. We will learn only the stepping stone method to find the optimal basic feasible solution. And that's all for today. Thank you.